Okay, I started the recording.
Okay, thank you, Galit. Yeah, today we're very happy. Thank you, everybody, for coming. We're very happy to have Ian Gemp, who is a research scientist at Google DeepMind. Thanks, Ian, to accept the invitation. You have 1 hour. You can adjust whichever way you want, if you want questions during the talk or not. And we will be around afterwards as well, as long as you have time to discuss further. Please take it away.
Okay, thanks. Yeah, and thanks for inviting me. Yeah, feel free to ask questions throughout the talk, or yeah, just yell at me if I'm not responding. I might not see the chat or something like that if you just post a question there. You can see my slides though. Okay. All right. So yeah, I'm going to talk about convex Markov games. So first, I'm going to start with some background and motivation for why we were even looking at this kind of framework. And then I'll talk about some of the properties that it has, define it, but specifically properties that make it a nice game setting to analyze and study. And then talk about why those properties lead to the existence of pure Nash equilibria. And then given that existence proof, we then try to establish an upper bound on exploitability. This is something that we want to be able to cheaply estimate to tell us how far a strategy profile is from a Nash equilibrium. And then using this upper bound, we then take the direct route and just minimize it in order to approximate pure Nash equilibria. And then I'll show in some experiments how this framework allows us to derive some interesting policy profiles. Okay, so like one of the, I guess the high level takeaway, if you had to take away anything, would be this table. So I'll assume everybody's roughly familiar with MDPs, Markov decision processes. So these are reinforcement learning problems where you have one agent and an environment. If you extend beyond one agent to two agents, you have Markov games or stochastic games. You can also think about these as under a different framework of occupancy measures as having linear loss functions for agents. If you replace that linear loss function with a convex loss function, you now have what are being called convex MDPs, although these have a long history too. And so we kind of looked at convex MDPs and at Markov games, and then realized that there's nothing at the intersection of the two. And so that is kind of at the most basic level what led us to look at convex Markov games. But at the same time, I'm on the game theory team at Google DeepMind. There were others that weren't sitting too far away from me that were working on convex MDPs and using these to derive exploratory policies in RL. They also then use these same concepts to try to learn, try to discover new plays in chess. Chess is obviously a two-player zero-sum game, but they didn't ever establish a framework really for thinking about this and studying equilibria in this setting. So that's kind of what led us to fill in this bottom right corner of the table here. Okay, but so yeah, I cited some old work for each of these. MDPs kind of were studied starting in the 50s. Same with Markov games and stochastic games. There's not an easy way to pin down a citation for convex MDPs. They arise from the studying the dual program of MDPs. So I've cited 2021, but it goes back much further. Collenberg was studying risk aversion in MDPs, and even further back, Takak realized, or a lot of people realized that there were non-Markovian settings that people wanted to study that broke the Bellman rule. And so you didn't have these rewards that were decomposing linearly across time, and that presented problems. First, I'm going to go over a little bit, just like some intuition as to why you would want to construct a convex MDP and what people are using it for. So one of the most popular uses is to encourage exploration. And this I didn't write on here, but I think Elad Hazan explored this in a paper in 2019. This specific instance of the problem, but people have also used this convex MDP framework to use it to imitate certain policies in RL, use it for risk aversion, robustness, and other uses. But okay, I just want to give a motivating kind of sketch. So imagine you're trying to, you want to maximize the entropy of your policy, thinking that that would lead to effective exploration of your environment. So that means we're going to try to maximize the entropy of the distribution over actions of our policy in every state. So if we do this, take this environment where you have a person that's in the left room. They need to go to this door in the middle of the room and use a key to open the door and get to the other side of the room. They actually don't need the key to get back if they want to get back. So this is like a one-way kind of door. If they're just using a random policy, they're going to eventually approach the door. They're going to like eventually jiggle the keys in the right sequence to open that door, and then they'll get over into the room on the right. But when they're in the room on the right, they're going to be using a random policy. Eventually, they'll get back to the door and they'll just walk through the door. So you can imagine they'll spend like 1,000,000 years in the room on the left, and they'll spend like one day in the room on the right, and you'll get this very uneven distribution over these two rooms, and so a very uneven distribution of exploring your environment. And maybe effectively they never actually get through that door to the right room, and so they never explore that room, and maybe that's where the treasure is, or that's where the actual reward is. Alternatively, there's this idea of thinking about RL in terms of occupancy measures, and so that is a distribution over actions and state. And so because it explicitly includes the distribution over state under a policy, if you go to maximize the entropy of the occupancy measure, you're going to directly encourage being in the left room 50% of the time and being in the right room 50% of the time. And so the only way to achieve that is to intelligently learn how to use the key to open the door. And so this leads to better exploration of the environment, or at least that's the motivation for why people are using it in different scenarios. And that's why it was used in this chess domain by Tom Zahavi and others. And they were calling this curiosity in that setting. Okay, so then just going to go over the definition of a convex Markov game. I think a lot of this will look as you would expect. So we have some set of players, n players. We have a finite state space S and an initial distribution over states. So we're going to start ourselves in the world in some random state. We have a finite set of action spaces, one for each player. We have a transition function, so given a state and a set of actions by all the players. When I say state, this is a joint state. You then get a probability distribution over next states. We have a discount factor, so this is going to be a discounted setting, discounted sum of rewards and generalizations. And then lastly, and this is the most important part, we're going to have a set of continuous utility functions where each is concave in the ith player's occupancy measure. And if these utility functions were linear in the player's occupancy measures, then this would just be a Markov game or a stochastic game. The fact that we're allowing more general utilities is what allows it to be what we're calling a convex Markov game, even though these are concave. It's just that we'll think about losses instead of utilities, but it's the same. And then there's a mapping that takes you back and forth between policies and occupancy measures. So to go from a policy to an occupancy is direct. So you can just think about roll out that policy, and then keep track of the counts of when you're in each state taking each action, and then normalize effectively. Doing the reverse direction, you don't necessarily have a one-to-one mapping. So if you take your occupancy measure over states and actions and you want to derive a policy, it should seem intuitive that you just need to normalize over all the actions that you take in the distribution over the actions that you take in a given state. So that tells you what your probability of choosing an action and condition on that state. But let's say your occupancy measure puts no mass on a given state, so you're never there, which means that like it doesn't matter what policy you take there or what policy you set there, because you're never in that state anyway. So you can choose the policy to be arbitrary in that state. And this actually will annoyingly arise in the math as something that we need to deal with. But yeah, so these are the two mappings back and forth. And then each player's optimization problem, given all of the other players' policies are held fixed, looks like a convex program. So what this is actually, can you see my, yeah, hopefully you can see my mouse. So as I said before, their utility function needs to be concave in their own occupancy measure. So it needs to be concave in mu I here. But their occupancy measure has to satisfy a constraint, and these are called the Bellman flow constraints. Essentially, any probability that you have flowing into a state needs to be equal to the probability flowing out of the state if it's a stationary distribution. This term in yellow does not depend on player I's occupancy measure, but it does depend on the other player's policies. And effectively, what we're doing here is we say, okay, if all the other players are held fixed, then just fold their policies into the environment and construct a new transition matrix that just looks at player I's actions and the transition between joint states. And so you can form this matrix essentially in yellow after you do that folding in of the environment. And then this term on the right depends on your initial state distribution. And yeah, so as you can see, this is just a linear constraint, AX equals B. We have this additional piece here that the occupancy measure needs to be non-negative. This term looks somewhat complicated, but it hides the fact that it also includes the constraint that mu needs to sum to 1. So it is a distribution. And you can derive that just by summing over states. You'll see that everything kind of cancels out nicely.
Ian?
Yeah.
One question. So players are choosing a pure actions here, or can they choose mixed actions?
They can choose mixed.
Okay. I was just thinking that the max over mu I guess you can achieve any mu I with a mixed strategy, I guess, but not necessarily with a.
Yes. Yeah. Okay. That's a great point. So if this utility function was just linear, then yes, the best response could be pure. But we'll try out utility functions that have entropy bonuses. And so then you'd have an incentive not to play a pure occupancy measure.
Okay.
And so this I just wanted to point out that this term here, where we're folding in all the policies of the other players, it involves a product of all their policies. So it's highly nonlinear. It's polynomial in the other player's policies. So this term is nasty in terms of pi minus I. And I should have said this notation is, that means all players other than I. But in terms of player I's optimization problem, in terms of mu I, their decision variable, this problem looks like a convex program. Okay. Okay, and so that was just setting up the problem. but our goal here would be to approximate a Nash equilibrium. And we're looking for a Nash equilibrium in terms of policies. And I think it's worth going into this real quick, because initially when we started working on this work, we thought of looking at a equilibrium in terms of occupancy measures, and it didn't occur to us at first that that doesn't make sense, because if you think about an equilibrium in terms of occupancy measures, it would mean that all other players hold their occupancy measures fixed, and then the focal player, let's say player I, checks to see if they can deviate and gain by switching to a different occupancy measure. But occupancy measures are distributions over joint states and actions. So if I'm keeping all the other players' distributions over joint states fixed, then that means that the focal player doesn't have the ability to change the distribution over joint state, which really limits their ability to do any kind of meaningful deviation. Since a lot of the time your reward might just depend on the joint state anyways. So I just wanted to point that out. So we're going to look for an equilibrium in terms of policy profiles, pi. And then, yeah, so this formula measures how much a player can gain by deviating to a different occupancy measure. Sorry, I should have spelled this out. This set M sub I just is a abbreviation for this set of constraints here. So these constraints, like I said, depend on these pi minus i's, and so that's why I've written try to find an occupancy measure z within the allowed feasible set, and yeah, this epsilon I measures the maximum a player can gain by deviating, and then the notion of approximation for Nash equilibrium is just taking the maximum over these epsilon sub i's. If those are all 0, then we're at a Nash. Okay, and then so this problem is written in terms of occupancy measures, but we can write it in terms of policies as well. So there's two things that are different when you write it in terms of policies. One is that every player is now, their decision variable is a policy, and there are no constraints now. Like every player can change their policy, and it doesn't matter. Their choice of policy does not depend on others' choice of policies. These are completely decoupled. Whereas player I's choice of occupancy measure, their feasible set depends on the other player's policies. So in that way, this formulation is an improvement. In another way, though, this utility function is no longer necessarily concave in player I's policy. It was concave in player I's occupancy measure, but not the other way around. And there is a matrix formula for converting from these policies, to these occupancy measures. But again, it has a nasty dependence on policies in it. So we have this joint transition matrix P that we then have to invert. This part is fine. Obviously, this would be linear in the player's policy, but player I's policy appears here too, and so it ends up being a nasty constraint. So if you were to formulate the problem in this way, you'd have to deal with these highly nonlinear utility functions, even though you have nice feasible sets. So this one has nice objective functions or utility functions, but coupled feasible sets. And we'll actually take advantage of these two properties to design an algorithm. Okay, so, oh, and I forgot to say, yeah, I had it right here, but I didn't say anything. So looking at this problem, we can directly appeal to existence results for mixed Nash equilibria from Glicksberg. So because this utility function is, we said it was continuous, and also this mapping is also continuous. So this utility function is continuous in pi sub I, and our sets are convex compact sets. So we get kind of mixed Nash equilibria for free. But what this means when we say mixed, is it's actually mixtures over policies. And so like mixtures over stochastic policies. And so this would be like having a distribution over two policies that are individually performing coin flips during their rollouts. And the distribution over these policies that's guaranteed by this theorem could be a continuous distribution. So this is kind of the approach that was taken in the paper that Tom Zahavi and others worked on. They use this policy space response oracles, or like population-based training approach to chess. And so they have to keep around checkpoints that they can then mix over. And in that sense, like equilibrium does somewhat trivially exist if you appeal to these older results. But it's nice from a practical standpoint if we can prove that a pure Nash equilibrium exists, because then we only have to keep around one checkpoint. Okay, so that's what we're going to aim to prove here, is that pure Nash equilibrium exists. Okay, so what I'm showing in this figure is the occupancy measure space for one player. And this player, there are two joint states, S0 and S1, and there are two actions, A0 and A1. And the like rainbow triangle region is the feasible set for that player. And ignore the arrows for now. And the black region, there is the best response set. So I haven't told you what the other player's strategy is, but in this case, our utility function is something like a ReLU, or has some ReLUs in it that force our best response set to have this like rectangular structure. So what it means is anything in that black set is a best response. That's kind of like so this is an example of a safety application where anything in that black set is safe. Anything outside of it has increasing penalty. Linearly increasing penalty. Okay, so that's just a picture of occupancy measure space. But what we're going to do now is we're going to think about what that looks like in terms of policy space. So we have this formula that takes us from occupancy measures to policies. And because we have to divide by occupancy measure in this denominator, it's going to be a nonlinear mapping. And so when we map to policy space, this is what that best response set ends up looking like in policy space. So it's no longer convex. It was convex before, which was nice. Now it's no longer convex. And you can think about like the equilibrium existence proofs, or Nash existence proofs, all rely on these fixed point theorems. So if this white dot is our current policy, we want our white dot to be in the best response set. So we want the strategy and our equilibrium profile to be in this best response set. But most of these equilibrium existence proofs rely on more stringent conditions. So, for example, Brouwer assumes that the best response is a point. And then Kakutani generalized that to saying the best response is allowed to be convex. So this would have been fine if it was convex. And actually, Dubrow, even though they didn't use this in their paper on abstract economies, which was in 54, they relied on a previous proof of theirs in 52. And I'm also writing Kozowski's name because this is somebody who's at University of Michigan who wrote a archive paper that I came across on like Nash equilibrium without convexity. And that's how I first stumbled on this line of work. But there's actually generalizes Dubrow's proof. But all that Dubrow required is that the best response set is contractible. And at a high level, all that means is that you can take this best response set and shrink it down continuously to a point. So effectively, it looks like somebody took, a small dot and then just like stretched it out. So it doesn't matter that it's non-convex. It just matters that it's essentially topologically equivalent to a point. And so that's the proof that we appeal to when we prove that Nash equilibria, pure Nash equilibria, exist in this game. And there was one more, I guess, when I was going through these slides, there's one more thing I wanted to point out. And I mentioned this would be an issue before, and that's this this mapping from occupancy measures to policies. So even if the utility functions, let's say they weren't just concave, they were strictly concave. So if they were strictly concave, that would mean that all our best response sets had unique best responses, so they would be singletons. But even if a best response is singleton in this space, it doesn't necessarily mean that it maps to a singleton in policy space, because if that singleton is on the boundary, it can then map to like an entire line in policy space. And in that case, we could then still rely on Kakutani, and I think we did in one of our versions of the archive paper. But it wouldn't allow us to handle utility functions that are concave and not strictly concave. Yeah. Okay. So that's kind of the general idea with proving the existence of Nash in this setting. Okay. Now we're going to derive an upper bound on exploitability, and this is using some techniques that we we used in an iClear paper from last year for normal form games, but applies to more general settings. Sorry, excuse me. Okay. So what I'm showing here is just a simplex for player I's action set. Player I just has 2 actions. And so this is its simplex. Say the current strategy is this xi of t, and say we derive a gradient for player I that is this black vector here. If you were just to measure the length of the black vector as kind of a proxy for telling you if you're at optimality or not, it wouldn't give you a meaningful result, in the sense that imagine your this black vector wasn't pointing directly up. Imagine it was pointing orthogonal to the simplex, so in the same direction as this 1, 1, 1 vector. In that case, player I would be stationary. They would, imagine running projected gradient ascent. You'd move off the simplex, and then you'd project back on, and you'd be at the same point. So player I has an epsilon sub I, if you will, of 0. But there's a more straightforward way of testing for whether or not player I's like effective gradient, which we'll call it projected gradient, is 0. So you can take this black arrow and then project it onto the tangent space of the simplex. This is the tangent space. And another way of saying that is you just do a vector rejection. So you take this black arrow and then you reject the 1, 1 vector, and that gives you this green arrow. And that is just a linear operation, a linear projection of this to the green arrow. And then if we measure the norm of the green arrow, and that is 0, that does tell us that we're at a Nash. There's, and at least all of this works in the interior, and this is in, I forget if I include a textbook citation here, but this is known in optimization textbooks. It does not tell us much at corners of the simplex, because you can imagine if this green arrow was translated to this point, and this was the strategy we're playing, the green arrow would tell us that there's room for improvement. We can go beyond 100% go beyond playing 100% of a certain action to like 110% and gain more reward, but that's not possible. So because we want to have like one rule that works for the entire strategy set, we instead avoid these pointers by adding entropy bonuses. So if we add an entropy bonus, we know that there is no equilibrium at the corners. In this case, these are no longer really Nash equilibria that we're searching for. These are quantum response equilibria. But we go a step further to show that, like in prior work, quantum response equilibria at low temperature are approximate Nash equilibria, and we precisely give a bound on that. Okay, so that's half the idea. The other half is that anytime you have a convex program or let's say concave program and there's a bounded set, you can upper bound the suboptimality with the diameter of the set and the norm of your gradient. Using the projected gradient just gives you an even tighter bound. So like if we're here and our gradient is pointing to the right, then we know that all the gradients as we make our way to the maximum are going to have a norm that's less than the norm of the gradient right here. So we can use the norm of the gradient right here as an upper bound for all of those, and multiplying this norm of this gradient by the diameter, which is greater than the distance from here to here, gives us an upper bound on our suboptimality versus this point. And I wrote gradient dominance condition. This is kind of not the same as a standard gradient dominance condition where you wouldn't have the diameter here and you'd have like a squared and there'd be some coefficient instead, but it's kind of like that. But using these two properties, we can derive a upper bound on player I's exploitability of their policy. So this you should recognize from the previous slide. So this is the diameter of the simplex, and this is the norm of this just means project onto the tangent space of the feasible set. These are the player I's occupancy measures. This is player I's gradient with respect to their utility function, or gradient of their utility function with respect to their occupancy measure, mu sub I. The tau here indicates that we've added an entropy bonus to their utility. So it's their original utility plus tau times entropy of their occupancy measure. And so this term measures how far we are from optimality of the QRE, since this is a entropy regularized game now. And then this term indicates the loss in approximation as we measure the performance of that QRE in terms of the original exploitability without entropy bonuses. And so this is the number of states times the number of actions is just the entropy of the uniform distribution if that was your occupancy measure, and then tau is the temperature that we use as a coefficient on the entropy bonus. So as this tau goes to 0, this term stops mattering as much, and you can just worry about this, although the Lipschitz constant of this will go up drastically as well if you're near a corner of the simplex. Okay, so then now that we have this upper bound, we're now just going to directly minimize it, and that's going to be, well, not there's another piece, but that's basically how we're going to try to solve for Nash equilibria. I should say that the setting here is that we were actually focused on n-player general sum games, not 2-player zero sum. Maybe it would have made more sense to focus on 2-player zero sum first, but we felt like we should just like lay out the general framework and an algorithm that allows you to approximate Nash in these games. This algorithm doesn't have guarantees, but it's it's based on well-principled algorithms from normal form games and extensive form games. Okay, so we're going to build up a loss function based on that upper bound that kind of tells us how far we are from a Nash equilibrium. I mentioned that there's this part where we project onto the tangent space of the occupancy measure set. And I apologize. I gave all of this intuition in terms of the simplex. We're not necessarily on the simplex per se. We're on some like subset of a simplex. But this whole technique of projecting gradients works for any set of linear constraints, not just the formula x1 plus x1 plus x2 equals 1. And I'll give you and this is the formula for projecting onto a feasible set that's defined by linear constraints ax equals b. And so you just take your identity matrix here. A is this matrix in yellow. And then you need to be able to invert A transpose. We prove that this is always invertible if gamma is strictly less than 1. And also all of this is differentiable as well. But so once you have this formula, like a sensible loss function is just to minimize the sum of the squared norms of all the players' projected gradients. And that's because if all of these are 0, then we're only paying this. And if tau is very small and all of these are 0, then we have a very good approximation to a Nash equilibrium.
Excuse me.
Yep.
Could I please ask whether the projection, does it ensure both that the sum of the distribution adds up to 1 and non-negativity, or just one of the two?
Okay. Actually, so the projection is acting on the gradient, not on the occupancy measure. So it's not. I just want to clarify that this projection is not a projection onto the feasible set.
Right.
It's a projection of the gradients onto the tangent space of the feasible set. So
okay.
Those don't obey the same equations. They actually like what you end up with for the feasible set is like x1 plus x2 equals 0 would be your equations for the tangent space. You can think of it as if you have x1 plus x2 equals 1 already satisfied, and then you were to add on like a delta x1 and a delta x2, then you'd want delta x1 plus delta x2 to equal 0 to ensure that the new x1 and x2 is still equal to 1.
Okay.
So it's yep. Okay, so then, yeah, we can formulate this loss function. Obviously, there's like lots of loss functions you could do instead. And we probably should have thought of that. The only reason we did this is because in prior work, we were trying to construct unbiased estimators, and this ended up being the most obvious way to do that. In this case, we're not going to be able to get an unbiased estimator of this loss, and so you could do anything here. Like we could have done the max over all these epsilon sub i's and used like, we don't need this term because it doesn't depend on the occupancy measures, but these. Okay, but then using this loss function, we can also translate to an upper bound on the exploitability of a policy profile in terms of our loss function, where n is the number of players here, and we're just using the like worst case occupancy measure over all the players. Okay, so then here's the algorithm. So you start with some initial policy profile. Actually, I think I should have said this. I think we always start with uniform, or most of the time, and some temperature schedules. So we're going to adjust the temperature of those entropy bonuses as we learn an approximate equilibrium profile. So at each step, you're going to try to minimize your loss function to give you a new equilibrium profile. Let's say you minimize to completion. And then in the next step, you change to a new temperature schedule. or new temperature, and you repeat. And just to give you an idea of what this looks like for a normal form game, this is so on the y-axis here we have inverse temperature. So when tau is 0, we have that lambda is infinity, or sorry, when tau is infinity, we have that lambda is 0. So this is, in this case, we're starting at the uniform strategy profile. There are 2 actions in this game. You either attend the bar or not tend the bar. This is the AlphaRoll bar problem. I think we have 10 players in this example, but we're looking for a symmetric equilibrium. So we're going to initialize to a uniform policy. We're going to solve for the equilibrium. It turns out, at infinite temperature, the equilibrium is uniform. Then you adjust your temperature, you resolve. Now you get a new profile. You adjust temperature again, resolve, and so on. And this plot just shows kind of the contour map. Luckily, this game has a nice smooth continuum of QREs that converge to this limiting logit equilibrium. It's what McKelvey and Palfrey, the inventors of the QRE, called it originally. It's not always, this continuum is not always this nice. It sometimes branches, it sometimes curves back. But in many cases, we find that it is possible to trace this continuum to a Nash equilibrium using this like simple procedure of optimizing and annealing temperature. Okay, and then now just to show experiments and like what this buys you. Okay, so we ran this on iterated prisoner's dilemma, iterated public goods game, iterated AlphaRoll bar problem. I assume everybody knows the prisoner's dilemma. And we compared against a number of other baselines. On the y-axis is exploitability. So going down to 0 means you found a Nash. Iterations are on the x-axis. And that's like the T in this algorithm. And we compared against directly minimizing exploitability. And so what I mean by that is every player actually solves their convex program to precisely measure the how much they could gain by best responding. We then used a library that's built on top of CVXOpt and JAX. And I should know the name of the paper. It's really impressive work. They allow you to backprop through convex programs. So that's what's happening in this black curve. We just directly minimize the exact epsilon of the game. Sim just means simultaneous gradient ascent for all players. So we know that this doesn't converge in general games, but we're running it anyways as baseline. And then round robin means we're going to cycle through the players one at a time. They're all going to perform gradient ascent steps. And what we see here is, so one, simultaneous gradient ascent, converge, or I shouldn't say converge. It is decreasing exploitability slowly. And it does this in the public goods game as well, and AlphaRoll, but it doesn't perform the worst. Our algorithm is in blue, and it does get down to very low levels of exploitability in each of these settings. I think I actually have an updated plot of this where it tracks these other two as well. But the directly minimizing exploitability does well until it hits around 2,000 iterations in each of these cases. It just fails because of numerical issues. Round robin, though, works well in all cases and gets down to 0 exploitability. But this is just showing you convergence to Nash equilibrium. In these games, there are many Nash equilibria, so we need to look at what equilibrium are these algorithms converging to. So in the iterated prisoner's dilemma, our algorithm converges to something that what I wanted to say here. Yeah, the utility per player is 0.47 compared to that of some other IPD strategies. So tit for tat is 0.5, so which is slightly better. Win, stay, loop, shift is 0.67, which is much better. 0.42 is worse than what we're converging to, and defect effect is the worst. That's the Nash of the stage game. And I think we kind of call that the Nash of a stage game is uninteresting in this iterated setting, but in this case, if it's worth looking at the actual policy. So if both players cooperated before, then you're more likely to cooperate again. That seems reasonable. If player one cooperated while player two defected, then player one feels burned and is actually going to change to defecting. If player one defected while player two cooperated, player one's actually going to switch to cooperating. They feel guilty maybe. And then if both defected, then they'll continue to defect. So at least in some sense, this Nash equilibrium is much more satisfying than the vanilla defect effect of the stage game. And that is actually what round robin is converging to. So even though like we see nice convergence of this, these green lines, in each case it's converging, or not in L for all, but in these two cases it's converging to boring policies. Actually, in public goods game, it converges to zero contribution to the public pot. In the iterated L for all bar game, what you get is this cycling of players. I think one player goes to the bar, and the other two players always stay home. So you get this asymmetry, and it's kind of an unfair solution. In the
sorry, just to clarify. So
Yeah.
the strategies here, they are history dependent?
Yeah, I'm sorry. The state in this case is the previous joint action.
So you
So
have
that-
one recall strategies here?
Yes, yeah.
Okay. And for green trigger, how come if they begin from cooperation, why don't they stay cooperating?
And then the other thing is that we use the uniform distribution over states. So we don't assume they start from cooperation.
Okay.
Okay.
Okay, I see. Okay, thank you.
Yep. And in this iterated public goods game, I think what I said before is a lot of the other algorithms were finding zero contribution policies. But in our case, I mean, this is very small, but the learned equilibrium profile had a per player utility of 0.03. So they were at least contributing something. So in each of these, I think the first half you could kind of summarize as, nobody's contributing or few people are contributing. If there's only one contributing, then we're not likely to contribute. But if two people start contributing, then we'll start contributing. If everybody's contributing, we're most likely to contribute. So that seems sensible.
How did you initialize these simulations? What policies were the initial ones? Always uniform?
Yeah, uniform.
Okay. Is it?
Yeah, I think.
Is it? Do you know whether the round robin kind of stuff? Do there exist other equilibria it could converge to for different initializations, or?
That's a good question. Didn't try different initializations, just tried uniform. But yeah, I guess the question is like, is this policy stable under round robin? So if I initialize close to this one,
does it somehow whether round robin is really is it always bad, or given that it converges faster and something?
Yeah. We ran on this grid world pathfinding problem. This was, I guess, just to show that coordination can arise from, even though it's a Nash equilibrium and there's no like explicit correlation, coordination can still arise because they can, because of the dependence on the state. And in this case, the state here is this grid world. So In this domain, this is a cooperative domain. So if agents receive reward when they both reach their respective states, so the green agent starts here and it needs to reach this green block. This is always the initial state, so we don't use uniform initial state distribution here. The blue agent needs to reach this top left block, but they have this path that they can't both cross at the same time. I'm just showing a rollout of the learned equilibrium profile over time. And in this case, there's some race to the shortcut. There is some stochasticity in the environment, so it's possible the agents choose an action, but they don't get their kind of requested effect. In this case, the blue agent won. The green agent then realizes, okay, I need to get out of the way, and goes down. Then once they're out of the way, the blue agent can get to their goal. Then once the blue agent is at their goal, the green agent can move over. So what's in this one is that there's coordination happening. What's interesting about this one is that the blue agent is actually choosing to go down instead of choosing just to stay at the goal state. This, I think, is the result of the entropy maximization objective, where it behooves them to travel to more joint states to accumulate occupancy measure there. But in the end, this one moves up to the blue state and they achieve their goal. And the red arrow is indicating the most likely action, and then the shading is indicating the probability of that action. So how certain they are about taking that action. And then lastly, or no, there's one more experiment, but in this one we used, so our utility function was the original reward in the environment, but then they were also being penalized for their KL divergence from some human policy that we grabbed from a different study, this Romero and Rosoka paper. And we're doing KL divergence to the occupancy measure that we extracted from that paper. And in this case, we were able to, in the rightmost column, this is iterated person's dilemma. And in the rightmost column is the human policy from that paper. And then in the this column is the learned profile. And I said that we were penalizing KL divergence to the human occupancy measure. We anneal that penalty over time, over the learning of the algorithm. And so it's essentially looking for the Nash that's closest to this human policy. It learns a policy that is quite similar. It maybe is defecting less often in this state where it's kind of betrayed, and equivalently in the state where the other might feel betrayed. It's defecting, once both players defect, it defects at a similar rate. But our learned policy profile has slightly higher utility, 0.48 versus 0.46. But maybe what's most surprising is that the exploitability of this profile, if you start from a uniform state, is 10 to the minus 4, whereas the exploitability of this human profile is nearly 0.5. And so it's interesting that you can slightly change the profile, but then drastically reduce the exploitability. So that found that to be an interesting experiment. I think this is not the last one, but I want to try to move through. So in this case, we took the Bok-Stravinsky game. We turned it into an iterated version of it where the state was the previous joint action. And the utility is to maximize your long-term reward, but then you get penalized if you both end up going to Bok more often than you go to Stravinsky, or vice versa. So it just penalizes the difference between these occupancy measures. In this case, we don't start from uniform because that would give us a boring solution. We randomly initialize the policies. And then over 10 trials, we found that the players were learning policy profiles that selected their favorite event at a rate of 60%. And they're achieving this squared penalty was at 10 to the minus 5, so it was at a very low number. Lastly, that synthetic domain that I showed you, this was the result of kind of like a...
Can I ask something about the BOS game?
Yep.
So do you understand correctly that if you randomize the starting point, it comes out at either equilibrium with equal probability, or do I misunderstood? Because there are two equilibria here, Bach or Stravinsky, and it winds up. I mean, do you let them learn jointly?
Yes, they're learning jointly. Sorry, I missed the first part of your question, though.
So the question is, you wind up at an equilibrium. That's what you're saying, right?
Yes, yeah.
And you should wind up at either equilibrium with equal probability. Is that correct? Or do you not test whether you, I mean, how often you wind up at either Bach or the other one?
So I guess what I'm saying is the equilibrium that they wind up at is, over these 10 trials, is always the same equilibrium. And it's, yeah, I guess the way I express this is that it seemed like 60% of the time they're ending up at one and 40% of the time the other. But what I meant here is that, so this player one prefers Bach. Their strategy at equilibrium is to select Bach 60% of the time and Stravinsky 40% of the time. And the Stravinsky player selects Stravinsky 60% of the time and Bach 40%. But that's the same for all 10 trials.
Yeah, I mean,
I'm not sure why, given random initialized policies, why it would be attracted to that same profile. So maybe I should check that. But that was the...
I mean, no, it's not the mixed equilibrium. If you say you wind up at either, I mean, what I don't going to get is, I mean, the trials wind up then at the behavior for both players, correct? And it will be a pure equilibrium.
Well, I guess what I was finding is that this wasn't a pure.
This is not a pure equilibrium, but is it even an equilibrium? Let me check. So
it's the mixed one.
It should be the mixed equilibrium, yeah. So what you're saying is actually a mixed equilibrium. So if the role player chooses Bach with probability 60% and 30%, so what I would find interesting is, I mean, this is very symmetric. What if you change the 1-3 to a 1-4 in one of the, because then you would more validate what the actual equilibrium is, because it could be due to symmetry that by accident it's actually a mixed equilibrium. Because it also happens to be 60% preferred relative to 20%, but that might not be the case if the numbers are slightly different in the lower box, because the equilibrium probabilities depend on the opponent's payoffs, not on your own payoffs.
Yeah.
So that would be interesting to observe. And I'm actually surprised that it's actually a mixed equilibrium, because that is, as a mixed equilibrium, it's very unstable. You should, I mean, expect as a behavior either one of the two equilibria.
Yeah, and maybe, so this could also be affected by, when we solve for this, so I wrote this utility here. I need to check the experiment, but because our solver adds in entropy bonus, it might be that we essentially start at uniform in our, or we start at random initialized policies, but we start with that entropy bonus in there, which might bring us towards uniform anyways, and then we end up looking for some equilibrium profile that's like near uniform. So
the problem is to make it up so symmetric between the two equilibria. Could be that it's quite misleading when you start in the middle, because then you're getting nowhere. I mean, for instance, dynamical systems could be replicator dynamics, could be other methods. They tend to converge to one of the two, pure equilibria, sorry. And it's better to test it with a non-symmetric pair of matrices. So it's like 3-2 and 1-4, or even 1-3 or whatever, but not the same in both, not the opposite.
Yeah.
So it's just a recommendation, because the symmetry might distort whatever you find out. It's not typical behavior.
Yeah, it's a good point. I need to go back to this experiment and check that.
Give it a try. Thanks.
Yeah. Thank you.
I guess another interesting thing would be to, given, like, if you want to achieve the mixed equilibrium, but it's unstable if you don't have that fairness constraint. I wonder if you can get around that by having also an annealing kind of parameter on the fairness thingy. And like, if even though, you know, if there's some speed for the parameter to go to 0 and you still achieve the mixed Nash, that would be kind of interesting in terms of the breaking that stability problem.
Yeah. There is maybe one thing that's worth mentioning is that because we're solving for an equilibrium as like minimizing this loss function, the dynamics of our algorithm are not like decentralized dynamics. So like an unstable, like a Nash that's unstable under replicator dynamics is not necessarily unstable under these under the dynamics of this loss function, because this is a potential. So everything looks like a star. There's no spiral. There's no, and even for like an unstable Nash, it won't look like a saddle point or anything either. So I think at least the way that we're solving for these Nash kind of gets rid of maybe a lot of the interesting dynamics that will kind of rule out maybe undesirable Nash equilibria. But I should look more deeply at this game, like you're saying, introduce some asymmetries and see what's happening, and even measure, you know, just confirm that if I switch to replicator here, this should be unstable in the code.
And not only that, I'm sorry, I mean, it's not only unstable, it's also even worse in payoffs, way worse than even the worst equilibrium for yourself. So because it's always a mixture.
Yeah.
I mean, you will not get two. You will get, really poor. I mean, it's because you have the zero signal with quite high probability.
Yeah.
And
I mean, if
it's even then, as the loss function, when you look at the payoffs, I'm surprised that it should. Anyhow, whatever.
Yeah. Okay, sorry. This so this last domain, I think I described in words that the utility that leads to this best response set looks something like a ReLU. It's essentially like a loss that is 0 if you're, you know, in some safe region, and then it linearly increases outside of that safe region. It doesn't represent any meaningful domain, or we didn't have any storyline behind it. It was just to visualize results, but we were able to solve for an equilibrium here. And in a sense, it's like easier than other settings because you have a large set for which you can achieve Nash. But we then looked up kind of a story for a different domain. This is a small like grid world MDP. And in this case, you have some robot warehouse. You have packages that are arriving off some conveyor belt. These robots need to go to this region to pick up the package and then bring it to the shelves. They are rewarded for moving quickly to get to the shelves and dropping off packages. But it's dangerous for them to be moving quickly in this slow region while they're picking up packages, because that's where all the robots go to pick up packages, and they could, there could be a collision. And so in one version of the problem, we include utilities that penalize the robots for using the fast action greater than like 10% of the time in this slow region. And in another version of the problem, we don't penalize them at all. And so that we found that if we don't penalize them, then they're moving fast 69% of the time. If we do penalize them, they're moving fast 42% of the time. And I mean, the only reason like this domain was really interesting to us is we wanted to, confirm, at least empirically, or try out using concave and not strictly concave utility functions. And so, we were able to kind of demonstrate in this simple domain. Okay, sorry, I'm over time. Conclusion, just in terms of takeaways, I guess what I at least personally found most interesting about this project, or like what the elevator pitch is, that we have Markov games, we had convex MDPs, we didn't have any thing at the intersection, so that's what we introduced. And then to actually prove that Nash equilibria, pure Nash, exist in this setting, we needed to use some more general techniques that allowed for non-convex best response sets. So I think, it's possible that could be useful in other game settings as well, as long as you have this kind of had this hidden convex program for each player, and then you have a nonlinear mapping back and forth. As long as that mapping is like upper hemi-continuous, you'll probably retain this contractibility of your best response sets. And then lastly, I pointed out a lot during the experiments that equilibrium selection is an important part. It's not just about converging to a Nash or finding a Nash, it's which Nash. All right, well, yeah, thank you for listening. Thanks for all the questions, and happy to take more questions.
Thank you very much, Ian. Very interesting talk.
Thank you.
Okay, let's open it up for questions, please. I have a question actually. So just based on the last thing you said about upper hemi-continuity of best responses, so I was wondering about if you have sufficient conditions for the pair of functions such that you get contractible BRs.
Yeah.
What would those be? What's enough?
Well, yeah. So I guess the only thing that I know is enough is that if you have a convex program. So, so maybe you are kind of limited in that respect. But let me go back. Okay, so so if we know that this each player's optimization problem holding everybody else fixed is a convex program, we know that their solution set is a convex set. So it means we're starting with a set that's contractible. And then if we push it through a mapping like this, which is upper hemi-continuous, then we know that that contractible set remains contractible. Now, the only way I can think of to generalize this would be to say, oh, I'm solving every player is solving an optimization problem that's more general than a convex program, but we still have this property that the best response set is contractible. We don't require that it's the best response set is convex, but I don't know a set of a class of optimization problems that people often work on that's more general than convex programs that still has this property of contractible best response sets or solution sets.
If we didn't have this two-step procedure to map back to policies, if you just look at whatever game, some pair of function that's continuous in your policy mixed strategy, I guess it's like hard to. I find it hard right now to think of is quasi-concavity. I guess that's already known that that's enough, right? Actually, I'm not sure for continuous games. That would be Glixberg, I guess. But
yeah, right. But I guess the Glixberg stuff. Like we don't have concavity in policy space, so that's why we had to do
right. It's much it's much better.
There's some. I mean, we've thought a little bit about it. I mean, there's like a definition of a hidden game here that's different than hidden games that people have already looked at. But yeah, I think we just maybe there's a way of writing like a follow-up paper that kind of generalizes this, but I don't think we know of any settings beyond this convex Markov game setting at the moment where it would apply nicely. So it's maybe not worth presenting it that way yet. But yeah.
Oh, very interesting. That's cool.
Thanks.
Thank you then. I'll stop the recording.